All right, so today we're going to talk about these GPS signal structures. So the signal that is being broadcast by the GPS satellite is just a sine wave. We talked a little bit last time about how it's a radio wave or an electromagnetic wave. So it's basically a sine wave. So here, this red line here is illustrating what's going on. So here's our GPS receiver on Earth. Here's our GPS satellite out in space, and there's our carrier wave. And the carrier wave is just an electromagnetic radio wave, and it's used to carry some information or code that is used to estimate the travel time of the signal. So the carrier wave is just a sine wave that's carrying a code. And let's just review a little bit about waves. One of the characteristics of waves that's really important that we use to distinguish different types of electromagnetic waves is the frequency of the wave, which is how many times the wave oscillates up and down per second. And each up and down is one cycle. And we describe frequency using the units of hertz, which is how many cycles per second. So if a wave is a high frequency wave, then we have lots of ups and downs per second. A low frequency wave has fewer cycles or ups and downs per second. So let's look, for example, at our radio stations. AM radio, if you tune into AM radio station 680, that's actually the frequency of the radio wave that's carrying that sound information to you. And that wave has a frequency of 680,000 hertz, which means that wave is going up and down 680,000 times per second. And it also could be expressed in kilohertz. So a kilohertz is 1,000 hertz, so 680 kilohertz. If you tune into FM radio 101.5, say for example, that frequency radio wave is coming at you at 101,500,000 hertz. So that's 101.5 megahertz or million hertz, so 101.5 megahertz. The other things we describe about a wave is its amplitude or height, and its wavelength, which is the distance from the beginning of one wave cycle to another. So you could measure it from peak to peak or trough to trough, or from the beginning of the wave cycle to the end of the wave cycle. So we have frequency, amplitude, and wavelength to describe our carrier wave. A wave with a higher frequency will have a shorter wavelength, and a wave with a lower frequency will have a longer wavelength. So all of these electromagnetic waves fall along the electromagnetic spectrum. And this nifty little chart here shows wavelength at the top in meters. And then the second level on the chart is giving you an example of how big that is. So let's see. So at 10 to the 1, we're on the scale of, so 10 meters. 10 to the 1 is 10 meters. Is about the scale, the wavelength is about the size of a house. And if we're at 100 meters, we're talking a soccer field. And if we're down here at 10 to the minus 10, we're at the size of a water molecule. So this is, over here is short wavelength and really high frequency. And all the way at the left of the scale is long wavelength and very low frequency. So these are the names, and we'll come back to those, the sources, and then we get down here to the frequencies. So you can see we're up at 10 to the 20, and this is cycles per second, so that's hertz. So 10 to the 20 hertz, or 10 to the 6, which is a million. All right, so GPS waves, those transmission signals, the carrier waves that are carrying the information from the GPS satellite, are on the order of 1,227 megahertz and 1,575 megahertz. So they fall right in this range, right in here, between an FM radio and a microwave oven. And just to give you an idea where your TV, if you're getting broadcast television, which not many people do, but if you don't have cable, if you have an antenna on your roof or on your TV, channels 2 through 6 are the frequency of waves from 55 megahertz to 88 megahertz. And then FM radio stations are 88 to 108 megahertz. And those are actually the station numbers that you dial into. Like if you listen to 89.5, that's the frequency of the broadcast of that FM radio station. This is the military's version of the electromagnetic spectrum, which shows us where we have VHF is very high frequency, UHF is ultra high frequency, and SHF is super. I don't remember. High frequency. And so here's where that radio spectrum falls in the whole electromagnetic spectrum. If we go to a little higher frequency, we get an infrared, which is our heat, and a little higher frequency, we get to the visible spectrum, then we get to ultraviolet, which is this is what sunburns us from the sun, then we get to X-rays, gamma rays, and cosmic rays, and these are dangerous for human exposure, right? All right, so the GPS carrier waves are in the band of radio frequencies called the L band, which ranges from 390 megahertz to 1550 megahertz. And new GPS satellites actually transmit electromagnetic waves at different frequencies. The older ones just are transmitting the L1 and the L2, and the newer ones include an L5 and an L3. The L1 is the one that we are using. That's the civilian frequency, and the Trimbles that we use and the Garmin that we use are all receiving the L1 frequency wave. The L2 frequency is used by the military, and it's also used in dual frequency receivers, which many survey grade, the higher accuracy survey grade receivers are dual frequency receivers. And what happens is the ionosphere, which is the upper part of the Earth's atmosphere, affects different frequency waves differently. And so the variation in that effect can allow you to remove some of the error resulting from the transmission of the waves through the ionosphere. So a dual frequency receiver is a higher accuracy receiver because it can remove some of the atmospheric error. There are also some new civilian codes that are being broadcast on the L2 frequency carrier wave, but our units are not capable of taking advantage of that. So for our purposes, we don't really need to worry about that. That'll be something that'll become more important in the future as there are more and more satellites broadcasting that code on the L2 frequency wave, and then we'll have more GPS units that are taking advantage of that. But for right now, we are using the L1 frequency carrier wave. So the carrier wave is a sine wave, and on its own, it doesn't actually transmit any information. So in order to get some information from the satellite to the GPS receiver, we have to modulate, or we change that carrier wave some way so that it can carry a code. And there are a few different ways that we can modulate the carrier wave, and we'll look at what how those work. So once you do this modulation of the sine wave, then you can transmit information. So one way to do it is just to turn on and turn off the carrier wave. So that's called pulse modulation. That's the simplest way to do it. Another type of modulation is what's called amplitude modulation. So remember, amplitude is the height of the wave. And so if we vary the height of the wave, then we can carry some information on that. And this is what AM stands for in AM radio stations. So they use amplitude modulation to carry the sound information to your radio receiver. Also, the picture part of the TV signal is transmitted via amplitude modulation. So you can see, let's say here's our sound wave that we want to carry. So that's our information that we want to carry. Here's our carrier wave down here. And what we're going to do is change the height of the carrier wave to match the sound wave. And so you can see here now we've got the amplitude varying of the carrier wave. So the carrier wave's amplitude varies according to the sound wave that's imposed on top of it. Here's another one where we've just got binary data, which is zeros and ones, and what we do is modulate the amplitude of the carrier wave depending on whether the value is 0 or whether it's 1. So we see the short wave height when the value is 0 and the tall wave height when the value is 1. So amplitude modulation is another way we can modulate a carrier wave to carry other information. Another way to do it is to modulate the frequency of the wave. So the frequency, remember, is how many cycles per second. So if we modulate the frequency, we either shortened the wavelength and increase the frequency, or we decrease the frequency. And this is, so FM is frequency modulation. This is what radio stations use, the sound portion of the TV signal, cordless phones, cell phones. There are a lot of wireless uses that take advantage of frequency modulation. And one advantage is that you don't have as much problems with static. So, so you can see here we've got a sound wave or some other sort of wave of information, and when impose it on our carrier wave, and so we end up with, we squinch the wave up here, we spread it out, we squeeze it up and spread it out, so modulating by frequency. All right, so the GPS uses what's called biphase modulation, and the GPS signal, the information that we want to transmit, which we'll talk about in just a sec, are a series of zeros and ones. It's called binary data, right? So it's either a 0 or 1, and it's a series of a bunch of different random varying zeros and ones. And so what they do is they basically flip the direction of the carrier wave when we switch from a 0 to a 1. So you can see here they've done a switch, here they've done a switch. So they're modulating the phase of the carrier wave. So that's how the GPS signal carries the information.